Hello, everyone. Thanks for joining today. My name is Gavin Hindman. I work at Intel's Open Source Technology Center. Today, I'll be talking to you about what Intel is doing to foster a robust open source community around time-sensitive networking. All right. A bit of an introduction to who I am. So I'm the Director of Engineering for Open Real-Time Systems in Intel's Open Source Technology Center. We primarily work on real-time Linux and other related technologies, TSN or time-sensitive networking, obviously being a key enabler. OTC itself is about 1,000 plus software engineers in Intel. We own the bulk of the Linux and open source enabling within Intel, with a few exceptions. And we work everywhere from BIOS and firmware up through the kernel to middleware applications and full OSs when it comes to Chrome and Android and a few other OS projects. Year after year, Intel is one of the leading corporate contributors to the Linux kernel. We're usually number one or number two, depending on what's going on at the time. My own background, I've been in Intel for over 20 years. About 15 years of that have been working in open source environments, starting with the first commercially available Linux preloaded laptops quite some time ago. The goals for today, talk about how embedded is changing in general, the external forces that are driving those changes, talk about the benefits of using open source software to grow these ecosystems, the OpenAvnu project itself, which is sort of the main open source TSN project at the moment, and what Intel is doing in general to advance the ecosystem and where we need your help. So TSN and Intel. Intel's been working in TSN for about 5 years in one way or another. We have the i210 Ethernet controller, which is a very widely adopted TSN-capable network card. It's got good support in the Linux upstream as well as other operating systems. For Intel, TSN is strategically important for enabling current and also, more importantly, the next generation of workloads that are coming, whether it's industrial infrastructure where you see lots of network consolidation and software-defined factory and edge devices, autonomous devices where you have machines interacting in a physical way with the external world, data center communication, and many other workloads. Really, TSN will take over just about every growing ecosystem, either whether it's wired Ethernet or wireless technologies, those come online more broadly. Open source itself is an important accelerator for broad market adoption. The industry, as we sort of see it now, is somewhat stuck with everybody building large proprietary stacks, having to maintain everything from the kernel on up. That doesn't scale. There's no differentiation in most of these features. They'll be ubiquitous cost of doing business features in the next 5 years. So having a well-supported, well-developed open source ecosystem to provide the core feature set makes sense for everybody. But that only works if we have the right abstractions and infrastructure in place. What's driving the switch over from traditional embedded? Really, the answer is complexity. I'm using a car example here, but the answer is the same whether you're talking about software-defined infrastructure, industrial automation, or anywhere else that has a growing need for compute resources. And the problem is really illustrated in the two diagrams there. Right? The current generation of cars, you have 100 plus independent ECUs going up into the hundreds. They're loosely federalized into a single system. There's more than 7 million lines of code. And the real core of the problem is these discrete ECUs are built and developed and certified independently of each other. And when they are all stuffed together into a single system, they're falling victim to unquantifiable emergent systematic issues. Anybody who's familiar with functional safety, you have the notion of systematic issues and random failures. And really what we're seeing in these large complex systems is what are truly systematic failures emerging as random faults because you can't test and find all of them. They're simply too complex to test away everything that you can find. For the next generation, complexity just goes up. As things consolidate into central compute systems, the functionality is 3+ orders of magnitude more complex. You have centralized workloads, which needs more compute, drives more opportunity for interference. And you have lots of secondary functions like sensor fusion, computer vision, deep learning that just add to the hardware and software complexity. Really, there's a number of core problems with these workloads, whether you're talking about traditional embedded or even worse for functionally safe systems. They are actively connected to an external world. Any of the security breaches that you've seen recently in cars and other semi-autonomous devices where the radio link to the outside world was the weak link in the system can show the problems there. And the current safety standards and processes don't really account for off-the-shelf software. They're designed for off-the-shelf hardware, but the assumption is that software is built from scratch for the safety application, and that does not scale to any kind of large system of any complexity. How this relates to TSN is that Ethernet will provide the high bandwidth backbone that will make all these use cases possible. Right? It has bandwidth, it has speed, it has low latency, it's relatively inexpensive. So it's really the solution of choice right now. It's fairly ubiquitous in industrial use cases. Automotive adoption is growing rapidly. I was at a TSN conference last month, and I believe it was that 16 of the major automotive manufacturers will have Ethernet in their cars within the next 5 years, if they don't already. And TSN is a key contributor there. Why open source software? In general, open source gets you to product faster and cheaper. If you have a well-supported ecosystem, you get earlier access to new hardware and features. You're not reliant on periodic drops from a vendor. Your internal engineering can be focused on differentiation on the top of a common stack. You're not having to build and maintain every piece of functionality you require to ship the product. In general, you have less dependency on vendors. To the extent that hardware and software manufacturers are writing to common stacks and common standards, you have some ability to interchange across vendors, and you don't have to go round trip through a vendor for every bug fix that you require. And generally, your software is more portable. One of the problems with the current RTOS ecosystem is that it's very much of a walled garden. If you develop your software for one RTOS, if you need to switch, the porting cost is generally quite high. Whereas with a modern operating system like Linux, the portability is very high if you decide to change distributions. Generally, with a well-maintained open source project, you have broad heterogeneous deployment and maintain stable trees, whether you're looking at the kernel or glibc or any number of the common user space projects across Linux. You see this kind of broad deployment and stable structure that will help build these products. You have community supported quality. Edge cases are exposed fairly quickly through broad deployment. When you have millions of devices running essentially the same software stack, the issues get thrashed out fairly quickly. And you have a discoverable history, which will be key for functional safety. The trend that we see in functional safety for complex systems is moving away from a traditional documentable failure case where you can provide argumentation to prove every failure point towards statistical argumentation that supports the likelihood of a critical failure happening within the time required for your standard. The only way you can provide that statistical argumentation is through discoverable data that you can mine and build trends and probabilistic curves. With open source, you generally get higher amounts of security through inspectability. Certainly, security itself has gone the curve over the last 10 years of security through obscurity into open source being generally the state of the art for security. Right? You have an army of researchers and independent engineers that are looking for security vulnerabilities in your code. And really that over time has proven the best way to have a secure and stable core infrastructure. So the downsides, you do have some dependencies, right? You have dependent independence. Yes, you're dependent on maintainers and other community stakeholders, either to provide you a bug fix or a feature that you're looking for, but you're not required to stick within those boundaries either. Generally, permissive licensing allows you to build proprietary derivative works. Anything GPL licensed is the obvious exception there. You can't fork the kernel and build your own product without contributing back. But in general, you're free to branch and fork any project at any time that it's not heading a direction that you care for. Obviously, that breaks the community aspect of the model, but you're not walled in. And in general, there's a long history and precedence of standards-based, community-maintained core stacks, whether it's the W3C, Internet Group, Kronos Graphics, any number of the media stacks that exist in Linux, and then the kernel itself, and glibc. How does open source relate to TSN itself? The OpenAvnu Project is the primary TSN open source project at the moment. It's sponsored by the Avnu Alliance, which is the TSN certification authority at the moment, and is a consortium of industry partners that want to see TSN be successful and be written to common standards. The project provides a collection of components for building TSN systems. It's open source, hosted on GitHub publicly. Most of the development happens in public, and is primarily licensed under the BSD license, which is very permissive. There are some driver and a few other pieces that are GPL licensed, but in general, it's a non-copyleft license. The core project was started by Intel around 2012 as OpenAvnu. That project was then adopted by the Avnu Alliance a few years later and became OpenAvnu. The project is in active development, but it could be more active. The graph on the bottom there is the overall contributions to master, excluding merges. So you can see it's a fairly consistent level of traffic since its inception. The spikes are some big project contributions, but overall it's a pretty consistent level of contribution. But we would like to see this grow and expand as more users come online and start using these components. This slide is kind of a snapshot and a discussion of where OpenAvnu is at right now and some of the issues with the current project. So it provides a number of core pieces at the moment. There's a driver, which is actually a fork of the upstream Intel i210 driver called IGB-AVB, which provides some direct access to the hardware queues. There are some helper libraries, a few daemons for time coordination, stream reservation, and coordination. There's some sample applications. So generally, TSN works on a talker listener sort of publication and subscribe model. So there are a few talker and listener examples. There's some helper scripts, and then there's a very large project called AVTP Pipeline, which is an SDK for building projects based on AVTP, which is a audio video transport protocol, which is one of the primary Ethernet protocols that TSN uses. Some of the downsides of the project as it is now is it's tightly coupled to the i210 fork driver. One of the goals of my team, as you'll see coming up, is to break that dependency. Our goal is to get the hardware portions of the stack down into the kernel where they belong. There's a large number of reasons not to bypass the kernel. The only downside to bringing in the kernel into the mix is that you do have some potential performance issues, and we're working to identify and optimize the stack to reduce those latency overheads as much as possible. Our feeling at the moment is that going through the kernel should be viable for the vast majority of people who want TSN use cases. There may still be some edges where they need direct access to the hardware, but those will largely be outliers from an industry perspective. This slide is really our vision for the OpenAvnu project and where we would like to see it evolve to over the next few years. So the high-level objectives in no particular priority order. Hardware agnostic infrastructure, right? This is not an Intel project. We're using Intel hardware since it is readily available and is well supported in the Linux upstream, but it's certainly not the only Ethernet device that can work with the stack that's being built. There are another number of other hardware vendors coming online and starting to look at what we're doing on the kernel side in OpenAvnu itself. Utilize, not bypass the existing network stack in the kernel. Our opinion is that any hardware configuration and shaper configuration should be done in the kernel, not in user space. That done for maintenance reasons, security reasons, a whole number of good reasons not to bypass the kernel, just from a maintainability, security, and stability perspective. Merge the changes in the forked IGB driver back to the Linux mainline kernel driver. This is actually already done. I'll discuss that in a bit. And identify and resolve any bottlenecks in the existing network stack in the kernel. And this work is underway now. The GitHub project itself is probably not optimal for people to pick up and just select the components they need for their particular project. So we want to restructure the GitHub project itself, and for things that we consider core components, start establishing those stable releases and maintenance branches so that the tip is abstracted away from the stable branches that are just taking bug fixes. Our goal is to have a number of product-ready shapers and streamers and daemons in the project proper. What's there now are certainly not bad, but they're mostly examples. They're very simple, not been qualified to any kind of product quality level. So our goal would be to validate things as far as possible in a fairly narrow number of use cases and hardware environments, so that you're roughly 80% of the way towards product in picking up those components. And the additional integration and validation and merging with the functionality that you care about for your product is the remaining 20% that needs to be done on top of the OpenAvnu project. Our assumption at this point is that the components will likely need to be safety certifiable. What this means from an industry perspective is still very much up in the air, but there are definitely trends towards using Linux and open source off-the-shelf projects for functional safety environments. As much as possible, we'll conform development at OpenAvnu towards these best known methods for certifiable products. It's likely not possible to certify them and probably not desirable to do so either in any formal sense. Generally, safety certifications need to be done in context of the product you're actually trying to ship. So an external certification would not likely get us very far. There's been a request from multiple projects at a higher level to have an abstraction API, a general TSN API at the user space level that they can write down to in order to access the Ethernet shapers and daemons that exist at the lower levels. We're working on that. In general, there's likely support needed for MCU class hardware. That's not likely something that Intel will work on, but obviously as other partners come online, they may provide MCU class hardware support. In general, most of what we're working on is not hardware dependent outside of the Ethernet card. So having a OS that runs on MCU class hardware will likely make things easier in general. We also want to provide a common repository for centralizing test cases and tools to accelerate compliance testing. As I mentioned earlier, Avnu is the primary TSN certification body at this point, so we will likely do some example certifications with the work that we're doing based on i210 or other devices, and whatever test cases and tools are developed in the course of that process will get pushed to the project as well. The last bullet is the main goal of this work at Intel, which is broad community participation. Right? These projects only will live and die based on the amount of adoption and participation by a broad community. Linux and other open source projects in general are littered with projects that started out well, never really gained any traction, and ultimately died because it doesn't make sense for any one entity to build and maintain solely an open source project. What specifically is Intel working on? Currently we're focused in a number of areas. The first one is not directly TSN related, but it's good to let everyone know about. There is an Intel production kernel project hosted externally on GitHub. This project is intended to be the latest LTS kernel with a number of back-ported features for future platforms. So it's essentially a vendor tree for Intel platforms. And the key piece here is that it does have a branch with the preempt RT, which is the real-time Linux kernel patch set already enabled. So feel free to go up to the wiki there. There's a lot more information there, and that will grow over time. We're focused on mainline kernel support for Intel integrated Ethernet controllers. Currently, I210 is in progress. Future devices will also end up in mainline and should support both the low-level TSN functionality as well as the user space stacks that are being built at OpenAvnu. We're working on the kernel infrastructure for network hardware and hardware shaper configuration. We submitted changes to add 802.1 QAV support, which is a credit-based shaper, to the Linux kernel. This bullet is actually already out of date. That work has been merged and should be in the 4.15 kernel, and that comes out later this year. And then we're working to characterize and resolve any latency and determinism issues in the kernel network stack. We know there are a few performance issues there that we'll need to nail down. So far, nothing has looked terribly worrisome. In general, it's not a stack that anybody has put much effort into optimizing to this degree. So there should be a lot of low-hanging fruit there to go resolve. We are working at OpenAvnu on some of the libraries and daemons. Wireless support is being added to the GPTPD daemon, which is the 802.1 AS time daemon. We're working on stream negotiation and handling. We're looking at libraries and example applications for streamers for support of a number of use cases. Automotive audio and video. We're also looking at Ethernet attached sensors and industrial command and control. So those are the three main use cases that we're looking at currently and plan to be working on over the next year or two. OpenAvnu examples and test apps. So there are a number of examples there currently. To the extent it's practical and makes sense, we'll port those current examples to the new kernel infrastructure when that becomes available and has been merged into mainline. And we're also investigating other opportunities for high-quality examples and test apps that can help move the industry forward. Where do we need help? In general, we need the same help that any other open source project needs, which is a community. This only succeeds if we have a large number of users doing the components, testing, sending back bug fixes when they find them, adding new features for the use cases that they want to support. For example, for the automotive audio use case, we're currently looking at just PCM audio for the initial streaming format, but certainly we'll provide infrastructure for people to add support for other codecs and video formats, and getting the community engaged in extending functionality will be key. The other thing that community involvement gets us is that ubiquitous deployment needed for functional safety. If you don't have a broad deployment of largely unchanged code, it's nearly impossible to build the statistical argumentation you'll need for off-the-shelf software. So this is a key component to the success of TSN in general and autonomous devices at large. And contribute back. As mentioned, test, fix, and contribute back patches. When you're building products, if you run into issues, don't just hold that fix in your own project. Contribute those back to the master project. Cross-architectural support. Obviously, we're focused on x86, 64. There will certainly be some ARM support, MCU class, MIPS devices, and any number of other architectures could be supported and should be as vendors come online. Volunteer maintainers, as the project grows, we'll likely need more people to help field and merge those bug fixes that come back from the community. So volunteer maintainers will be key. Obviously, this gets big enough, we'll need to discuss larger funding and partnerships and those sorts of things, but that's not the case right now. It's essentially a volunteer project for people that aren't being employed to work on it. Streamers and libraries for additional use cases, as I mentioned previously. We're looking at industrial command and control, but there's a whole world of other use cases that can be built on top of TSN that could have examples and components pushed to the Avnu project. Software shapers, primarily what we're working on right now is hardware-based shapers, but for smaller, less expensive, less latency sensitive systems, software shapers may make sense as well. And then example applications to make use of those use cases. All right. Thanks, everyone, and have a good day.